Okay, hello everyone, and welcome to the fifth session in the online lecture and interview series of the Techfest 2020 of IIT Bombay. Okay. Hello everyone, and welcome to the fifth session in the online lecture and interview series of the Techfest 2020 of IIT Bombay. Okay. Hello everyone, and welcome to the fifth session. Technical folks, I'm getting some echo. Is it something at my end? Technical folks, I'm getting some echo. Is it something at my end? Okay, let's start again. Hello everyone, and welcome to the fifth session in the online lecture and interview series of the Techfest 2020 of IIT Bombay. Good morning, Professor Cerf. I am Professor Varsha Apte from IIT Bombay, and on behalf of the organizers of Techfest and all our listeners, I welcome you to this session.
Thank you very much. It's a real pleasure to participate in this conference, especially considering that it's an online affair and all of us are experiencing increasingly the opportunity to participate in events that we might otherwise not be able to attend. So I'm here from the convenience of my basement office in McLean, Virginia, and looking forward to our discussion.
Thank you for being here, sir. Many people have contributed to the questions I'm going to ask you today, and I'm honored to be the one speaking with you on behalf of the student organizers, my colleagues and friends who suggested many of these questions. So let me start right away with a thought that you already said and which is on everybody's mind today, which is that we cannot thank you enough for inventing the technology, which is TCPIP or internet as it is commonly referred to, that has kept us sane and informed, entertained and connected to our near and dear ones when they were not really near us. So looking back, 40, 50 years ago, what do you think, what would you name as the one thing or the top few things that made this technology, the TCPIP, survive and flourish for so long, especially when so many other really hyped technologies came along and didn't survive? What made TCPIP the one?
So I think there are several reasons why this technology has had such a robust life. But let me start out by telling you that one of your countrymen was very much involved in the development of the TCP/IP protocols. His name is Yogan Dalal. His parents were diplomats and were all over the world. But Yogan ended up at Stanford University as a graduate student in my laboratory. And the project began in 1973 when my colleague, Robert Kahn, came out from the Defense Advanced Research Projects Agency and told me that he had a problem. He had multiple packet switch networks, a satellite net, a mobile radio net, and the ARPA net, which is a wireline system. And his problem was how do you connect them all and make it look uniform? So Yogan and Carl Sunshine, another one of my graduate students, and I took the original protocol that Bob Kahn and I described and then made a detailed specification, which was published in December of 1974. Now, I promise you I'm not going to go through the entire 50 years of history here, but I wanted you to know that one of your countrymen contributed very, very deeply to the development of the protocol. The reason that it has been so successful and robust, I think, is in part because we were able to spend a great deal of time testing it and fixing it, evolving it. We went through 4 iterations of the specification before we sort of froze the design in 1978, and then we began implementing it on a variety of different operating systems. So there was a lot of operational experience with the protocol. The second thing that I think contributed to its longevity and robustness is its simplicity. It was a very, very simple protocol. It was a layered architecture, which we had learned to do from the ARPANET project, the predecessor to the internet. But the important part was this thing which we call the internet protocol, which was, if you looked at the stack of protocols, that it was the thin waist of a kind of an hourglass-like shape. And everyone had to do the internet protocol because that's how you labeled packets to say where they were supposed to go and where they were coming from. And so we had to invent a global addressing structure. And we thought our way through this and decided against using country codes for the addressing system. We wanted it to be non-national in character. And of course, we were motivated by the fact that this was supposed to be the basis of a Defense Department command and control system. It had to work in every country. And we certainly didn't want to have to get permission from every country in the world to have addresses so we could operate our global command and control system. So we made it completely non-national in character. It was purely topological. That was a very deliberate design choice. The other thing that characterizes the internet layer of protocol is that the packets don't know how they're being carried. So if you read the internet protocol spec, it says nothing about any of the underlying transmission technologies that are supporting the basic packet layer. And that turned out to be important because we knew that there were going to be new technologies coming after 1973. And we didn't know what they were, but we assumed that they would come. And so we wanted the protocol to be insensitive to any knowledge of the underlying system. And some engineers argued, well, you should fine tune the protocol to the underlying transport structure. And we said, no, we didn't want to do that. And that's helped a lot because new technologies have come along seemingly every year to support the internet protocol. So that's a very important design decision. A second design decision had to do with the fact that the packets of the internet don't know what they're carrying. They know that, where they came from, they know where they're going, and they know they have a little bag of bits that they're carrying with them, but they don't know what the bits mean. And that's important because what that implies is that if you have a new application that you want to build, the network doesn't have to change because it knows nothing about applications. The edges of the net where the computers are know about the applications, know how to interpret the bits, but the network itself does not. Ironically, the three networks that made up the original internet, a packet radio net, a packet satellite net, and the original ARPA net are all gone now. And yet the internet persists because it's not so much a physical thing as it is a design and an architecture and a set of protocols. And as long as you can implement those in any network that you build, you can plug in and become part of the net. The last point I will make is that we made no assumptions about business models. We didn't make any assumption about on what basis any of the networks of the internet would operate. Some could be not-for-profit, some could be for-profit, some could be private networks, some could be government-operated networks. We didn't care. All we cared is that they had to meet all these protocol specifications and then find somebody to connect with under whatever terms and conditions you could negotiate. And so we left it extremely open. And of course, we were also open to new protocol design, and the layering allowed you to put new protocols vertically or new protocols horizontally. And they came during the course of the last 50 years. Many new protocols have come along and have been fitted in to the architecture without disrupting everything else. So I won't go on on this, but the point is openness and super flexibility and simplicity. And I can tell you those have conferred a substantial degree of robustness and also freedom to invent new applications and new protocols.
Absolutely. So the flip side of this question is that if you could look into the future in the 70s, if there was some note that you could have found in your pocket that the future you gave it to yourself, and you knew what was coming up in 2020 or such, what is the one thing or the top few things that you would have changed back then in the design of TCP and IP?
Well, there are three things. The first one, of course, is everybody knows that when Bob Kahn and I did the original design, we picked an address space that fit in 32 bits.
Hmm.
2 to the 32nd is something like 4.3 billion terminations, although we never expected that we would have a 100% densely assigned address space. But if it had been densely assigned, it would be 4.3 billion addresses. And that was more than there were people in the world at the time. Well, looking back, we know now that we needed the larger IP version 628-bit address space. To be honest, I don't think I could have convinced anyone, including myself, that we actually needed 2 to the 128th addresses in the address space. So I probably could not have avoided the transition from IP version 4 to IP version 6. The second thing is that public key cryptography has turned out to be a very important component of internet security. It's certainly not the only thing, but it's a very important part, especially for key management and for shared key generation. The problem, of course, is that public key crypto was only hinted at in 1976 in a paper that Whit Diffie and Marty Hellman wrote called On New Directions in Cryptography. And at that point, I was at DARPA and I was running the program and eager to get to the point where we could stabilize the protocol specification and get implementations going so we could see if it worked. So although I was very attracted to the concept of public key crypto, I didn't have any algorithms available at that time to implement it. So I ended up using some more conventional symmetric key algorithms, and some of them were classified, and I couldn't share that information with a lot of the people who were working on the internet. So it turns out that we didn't get public key cryptography into the system until somewhat later. But those students who are looking at the history anyway will see that we had included in the design provision for end-to-end cryptography. IPsec was one of them. Eventually, we also ended up with TLS, which went by other names, and now QUIC, which is a protocol introduced by Google, which has a cryptographic component to it. HTTPS, of course, is very dependent on public key crypto. So the good news there is that we could retrofit it into the system. Now, there is a third thing, and this one is really painful because it is an absolute blunder on my part. When we designed the packet radio system, we designed it for mobility. We allowed the vehicles to move in the space where we had repeaters up on the mountaintops and we had other towers. And the system worked. Would assign an IP address, and then the IP address would be mapped dynamically into routes in the radio network. And even though the topology was changing over time, we kept track of that. So the IP addresses were bound to dynamically changing routes in the packet radio system. I thought, okay, we handled mobility, done. Wrong. It turns out that I didn't think about the problem of moving from one network to another, having to change the IP address. And as soon as you change the IP address, TCP connections break. That's for another awkward thing, is that I bound the TCP protocol and the IP protocol together to save some bits. Otherwise, I would have had more header bits in the TCP layer. And at the time, I was very sensitive to how many bits were in the header. So that was really a serious blunder on my part, because it meant that the TCP/IP connections break when you change the IP addresses. Fortunately, the QUIC protocols, which come from Google more recently, are a combination of TCP, TLS, and then riding on top of UDP, which rides on top of IP. And it turns out the mechanisms that are used there would actually allow at least one of the IP addresses to change and allow the two parties to get reconnected again, because they share a common cryptographic variable that they can use to identify themselves to each other. So if the connection breaks, they can reconnect even if one of the IP addresses breaks. If both of the IP addresses change, it doesn't work. But I wish that I had been more attentive to that problem. And of course, now we have a partial solution to it.
Okay, so addresses, security, mobility. That's sort of the summary of your.
That's right.
First two were still handled, but I mean, the second was handled, but address space and mobility is something that if you had a future look into it, you could have done differently. So let me move on now to a little more general question that if there is a general audience that has tuned into this interview, they would be interested. Um, so we talked just now about all the immense positive impact of internet from healthcare, education, just connecting to loved ones and everything. But for every positive impact of a typical scientific engineering invention, there is a usually an equal and opposite undesirable impact. One of the ones that comes to mind recently, which the internet seems to have almost enabled, is these social media applications that very easily promote fake news, very quick forwarding. I mean, the fact that it's also fast and so resilient is can be used to ensure that undesirable news, fake news propagates. Our thoughts get onto the internet in a matter of a few seconds. We don't have time to think about anything. And extreme opinions get clustered and echo chambers get created. So is there anything, is there an engineering solution to either the social media layer or the internet layer itself? Is there an engineering solution that could promote interactions, meaningful interactions rather than trolling, reasoned discussions rather than echo chambers, real discourses and ability to ask questions and so on, rather than what we see is happening now? Can the internet support that?
So I wish that I had good news for you and could say that there are technical solutions to this problem. But I have to remind you that even in face-to-face interactions, we have disagreements with each other, and some people are quite obstinate in their opinions and they're not ready to change. In fact, we've learned, this is something that's important, by the way, that students who are studying mathematics and computer science and artificial intelligence and networking and things like that should appreciate that we should be paying attention to social and economic behavior. We need to talk to psychologists. We need to talk to neuroscientists. We need to understand how our brains work and how we think, because a lot of the behaviors that you're describing are a direct consequence of the way people behave and have not so much to do with the technology of the platforms. The platforms are essentially neutral on the whole. Now, I will come to some points about social networking where there is less neutrality than one would like. But let's just start by understanding that people are people and they behave in quite diverse ways. That's why we still read Shakespeare. Can't say whether Shakespeare is popular in India, but he's certainly popular in English-speaking countries. So, and we learn from him that people are terrible. I mean, they do all kinds of bad things. So let's look at the situation we're in. The neutral internet platform and the relatively neutral World Wide Web platform has enabled, as you say, social media. And the social media have applications which, in my opinion, exacerbate the kinds of extremism that you were describing. And the reason for this is that the reward system in the social media reward extreme statements that get a lot of attention. Exactly. And so it's the attention getting aspect of the reward system which needs to change. At the moment, you're rewarded by the more likes that you get, or you're rewarded by the more views that you get, or you're rewarded by the more followers you have. And the problem is that often people will be attracted to something that is extreme, either left or right or something else. So we need to work on that. That's a matter of policy. And although I don't want to make this overly simple, because you could establish a policy that says that you reject extremism in the social medium. The question is, how do you detect it? And how do you filter it out? And how do you avoid ending up being censoring unnecessarily and too much? In fact, there are some regimes you could imagine where censorship would be a highly desirable feature. I would cite China as an example of a place that's been very focused on finding ways to limit the kinds of communication that its citizens are able to accommodate either within the country or going outside the country. So we don't, those of us who live in democratic societies don't want to end up facilitating state censorship. But at the same time, we're concerned about the harmful propagation of misinformation and disinformation. Now, scale turns out to be part of the problem. At Google, just to pick something I have a little knowledge about, we get about 400 hours of video uploaded into the system per minute. Just think about that, 400 hours of video per minute. And so there's no way that we can introduce human beings to review the material. Fortunately, we've invested heavily in machine learning, which is a technology which has emerged over the last 10 or 15 years in pretty dramatic ways. And so we're using machine learning to try to help identify material that we should filter out. But it doesn't always get it right. It's brittle, it's biased based on the training sets that we may have used in order to train the machine learning algorithms. So in the end, I think the only way we're going to solve this problem is to apply 3 or 4 different techniques. One of them is technology to detect and filter out what we might consider to be harmful content, misinformation, disinformation, and the like. The second thing we could do is to say that we have terms and conditions of our service, and if you violate them, there will be consequences, like we'll cancel your account or filter things out. Of course, we won't filter everything out. It's like the rule of law. The law says, if you do these things, or maybe it actually says, if we catch you doing these things, there will be consequences, but we won't catch everybody. That's also true of some of these filtering tools. So then the third thing you could say is, don't do that. It's just wrong, and try to exercise moral suasion. That sounds very weak in a way, but I think you would appreciate this. Gravity is the weakest force in the universe. But if you have enough mass, it's quite powerful. That's why the sun keeps the Earth in its orbit. So when you have enough in the way of social norms in a large society, then the pressure, social norm pressure, can be used to essentially cite better behavior, not necessarily perfect behavior, but better behavior. So those are several things that you can imagine applying in order to deal with the problem. There's one other thing you could do, and that's to use the wetware up here to think about what you're seeing and hearing. We call this critical thinking, and those of us who are scientists are very aware of this, because that's the scientific method. You have a hypothesis and you do experiments and you see whether the hypothesis makes any predictions that are useful, and if it doesn't, or if the measurements essentially falsify the hypothesis, then you, as a good scientist, you have to throw away the hypothesis and find a new one. So getting people to think critically about what they're seeing and hearing is actually a good thing, but that takes work, and not everybody is willing to put the work into asking questions like, where did this come from? Is there any corroborating evidence for the statements that are being made? Is someone trying to manipulate me to get me to make a decision that I don't want to make? So we have to keep encouraging people to think critically about what they see and hear. We want young people especially to learn this as a normal style of thinking, so that when they grow up and they're confronted with all of this information and misinformation and so on, that they will be able to do their own filtering up here.
Yeah. Okay, let me come back to a little more hardcore engineering question, maybe for our college students who have tuned in. So I believe you have been working on interplanetary internet.
Yes.
So what are the needs? What are the human societal needs that are really driving that exploration? And consequently, what would a network look like? An interplanetary network. What are the
So
challenges? What are the new
thank
challenges?
you for asking that. This project has been going on since 1998. Uh, in 1997, the Pathfinder mission landed successfully on Mars after something like 30 years of failure. No, I guess 20 years of failure, because the previous successful missions landed in 1976. And in 1997, we get the Pathfinder land. So the following spring in 1998, I was at the Jet Propulsion Laboratory with some colleagues, and we started talking about the nature of communication in space, and observed that almost all the missions had used point-to-point radio links in order to get data back and to send commands to the spacecraft. And we thought, what would happen if we had a whole network, something like the internet, that covered the solar system? Wouldn't that be helpful to space exploration, whether it was either manned or robotic? And so we said, well, that sounded like a good thing to work on. So we began thinking our way through what a network, an interplanetary network, would look like. And we thought we could start out with TCPIP because it worked on planet Earth, and we figured it would work on Mars. And then we started doing the math. And the distances between the planets is literally astronomical. And if you do the math, you discover that the speed of light is too slow. Between Earth and Mars, when we're closest in our orbits, we're still 35 million miles apart. So it takes 3.5 minutes for a signal to propagate from Earth to Mars. And when Earth and Mars are farthest apart in their orbits, it takes 20 minutes for the signal to propagate one way, and of course, another 20 minutes to come back. I can guarantee you that TCP was not designed to deal with a 40-minute round trip time, and it gets worse as you go to the outer planets. That was problem number one. Problem number two, the planets are rotating, and we don't know how to stop that. So if there's something on the surface of the planet that you're talking to and the planet rotates, eventually you can't talk to it because it's on the wrong side of the planet. And same problem with some of the orbiters. So what we had was a variable delay and disruption environment in which to design and build protocols. So we said, okay, we have to start over again and think about protocols that will work in this more hostile environment than the internet works in. And so we, in fact, came up with a new delay and disruption tolerant networking protocol we call the bundle protocol. It's layered just like the internet is. There are low-level protocols and higher-level protocols, application protocols. They are now being tested. They have been standardized by the UN Consultative Committee on Space Data Systems, which is made up of all of the spacefaring nations. The most recent protocols are on board the International Space Station. The prototype of these protocols was actually uploaded to Mars in 2004 because the rovers that landed, Spirit and Opportunity, were supposed to transmit their data directly from the surface of Mars back to Earth to the 3 antennas of the Deep Space Network. These are big 70-meter dishes. One is in Canberra, Australia, one's in Goldstone, California, and one is in Madrid, Spain. But the radios on board the rovers overheated, and everybody said, "Don't transmit. You don't want to destroy any of the instruments that are on board." So one of the engineers noticed that there was another radio available. It was an X-band radio that could reach the orbiters that were very close by in orbit around Mars that had been set up before the rovers in order to image the surface of Mars, so we could figure out where the rovers should go. So we reprogrammed the rovers and the orbiters with the prototype interplanetary software. And so since 2004, all of the data that's come back from Mars has come back through the interplanetary protocols, including new spacecraft which have landed subsequently. So there was a Phoenix lander that went to the North Pole, and there was, in addition to Spirit and Opportunity, there was Curiosity, and there was the Mars Science Lander, and now there's another one going. I forget, Persistence or something. So anyway, the whole point here is that the protocols are getting rigorous testing. They've been implemented in a number of different operating systems. We even have implementations for mobiles. And we have a group in northern Sweden that's testing this kind of architecture with to keep track of the reindeer that are, we got radios hanging around the necks of the reindeer to keep track of them. What's important about the bundle protocols is that if you don't have a link to transmit to right away, instead of throwing things away, which is what happens with TCP, you actually remember it and hold on to it until the link comes up. Because for many of these space-based links, they come and go based on orbital motion. And so you can actually predict when the next contacts will come. And so we organized the protocols to hold on to data in the network until the links could come back up and you could transmit. And there are a number of other details, but I'll leave those for now. So the exciting part is that it's actually in use. It will be used on the Artemis program, the return to the moon that the US is undertaking, and the Gateway program. But the protocols are freely available. The specifications are open. Implementations are available on GitHub. So we're hoping that this will become a part of the future of space exploration as time goes on. And of course, as we send each spacecraft out, eventually, if it completes its mission, we could repurpose the spacecraft as a node in an interplanetary network. And so you can imagine over a period of decades that the interplanetary network would simply grow over time.
Okay, I think I may have like 30 seconds for one last question, unless the team tells me not to, I'm going to ask that. So we are experiencing the consequence of a pandemic like we have never seen before. And it seems like an uncontrollable biochemical virus. Now, do you think there could be a similar, quote, pandemic in the digital world with a digital virus, possibly powered by AI, which can spread through this hyper-connected world through the extremely resilient network that we have, and with all of the data that is stored? Do the current network and computing engineers need to start working on building the, quote, immunity of our networks and maybe start developing a vaccine for a digital virus?
Well, you put lots of things into that question. So let's see. First of all, you notice that we use the same vocabulary for digital vulnerability as we do for human health vulnerability. So we talk about viruses, we talk about propagations. And it turns out that we really do have a problem. We have buggy software, which we haven't learned how to fix. We even, unfortunately, have tended to implement software that has bugs in it that we don't notice until it gets propagated. And so this is very embarrassing. It looks to me like we need to get our computer scientists to learn how to write software that doesn't have bugs. We probably need better software programming environments to try to reduce the bug level. And I worry about this not just from the standpoint of malware, deliberate attacks on those vulnerabilities, but I worry about software that's just in ordinary devices. We hear about the Internet of Things, and they're simple things like refrigerators and toasters and ovens and things like that, or air conditioning systems. And we've already seen cases where someone has been able to penetrate the software and then repurpose the computing equipment to form botnets, which are used to do service attacks or generate spam or propagate viruses and other kinds of malware. So it's a huge mess. We have a lot of work to do to try to cope with that. And my guess is there's plenty of room right now for research to try to reduce the level of vulnerability that we have. Now, some of this is just human behavior, like usernames and passwords. In fact, just before we got together on this link, I was configuring two devices that are used for second factor authentication to one of my accounts in a banking system. And so this is a cryptographic second factor in addition to my username and password. And I'm really very comfortable with that technology because I know that even if somebody gets my username and password, I have a physical device that the other party doesn't have that has a cryptographic authenticator in it. So it makes me feel safer. And I believe correctly that it does. I am safer as a result. So we have all of those hard problems to deal with. And then we also have, of course, the problem of digital information in general and how to preserve it over long periods of time. And we don't have time to dive too deeply into this topic. I will just point out that historically, the means by which we have recorded information has tended to have shorter and shorter lifetimes over time. So you imagine going back to the Babylonian period, the Assyrian period, you find these baked clay tablets with cuneiform. And if you can still read cuneiform, which very few people can do, those tablets are still meaningful 5,000 years later. And then you get vellum, which is made with sheepskin or goatskin or something, and that stuff can last a couple of thousand years. And if you've ever seen a vellum manuscript, it's sometimes as beautiful now as it was, 2,000 years ago. Then we get rag paper, then we get wood pulp paper, and now, of course, we have these digital media. We're lucky if those digital media last 10 years or maybe 20 at the outside. So our problem is the media are not very stable. And even if the medium is readable, we may not find a reader for it. So, look for a 5.25-inch floppy reader. That's not too easy. You might find it in a museum. So if we're trying to preserve digital content, we're going to have to keep writing it in new media so that we can preserve the bits. But we have another problem. What do the bits mean? And usually that means a piece of software has to look at the bits to tell us what it means or to render it if it's an image or a video. So now we have to find a way to preserve software that knows how to interpret the bits. But that software relies on running in an operating system. And that means we have to preserve the operating system, but the operating system relies on running on a particular piece of hardware. So now what? We can't keep the hardware forever. So now we have to figure out, how do I emulate the hardware so I can run the operating system, so I can run the application, so I can interpret the bits of a file that I wrote 25 or 50 years ago. And you can think of applications that need this longevity: financial systems, healthcare systems, real estate transactions, all kinds of things require longevity. So we have an awful lot of work ahead of us in the digital age in order to cope with all the various fragilities that digital age visits upon us.
With that, Professor Cerf, I think it's time to end the interview. I would like to thank you very much for joining us. And I really learned a lot. I have been teaching networks for so many years, but 25 minutes with you, I have learned a lot. And I hope that everybody else has also learned a lot. Thank you very much again for joining the session.
Well, thank you for inviting me to join you. I certainly enjoyed our chat, and I look forward to more of them in the future.